Hi everyone, welcome back, and this next lesson is still about slope fields, and this time we're going to look at a slightly more complicated example where our differential equation says dy dx equals x times y. Now, rather than drawing out a table of these things, it's probably easier just to go directly to the grid. So let's imagine we're looking at the origin here. So x and y are both 0. 0 times 0 means I have a gradient of 0. Let's go up to point 0, 1. Again, 0 times 1, 0. It's literally just the product of the x and the y coordinate at each point. Again, 0 times 2, 0 times 3. So it looks like we've got 0 gradients everywhere up and down the y-axis. Again, here we're going to have 1 multiplied by 0, 2 multiplied by 0, 3 times 0, 4 times 0, and so on. Actually, I might just only go to positive and negative 3, not all the way out to 5. Now, what happens when we get to somewhere like here? Well, x is 1, y is 1, so the gradient is 1. But when we get to here, x is 1, y is 2. So I'm going to have to go from this point down to there. That's a gradient of 2. Here I have a gradient 3, so I'm going to have to be aiming, and now that line there is a little bit too long. So when I get to this one here for 3, I'm going to have to be going all the way down to there, aiming for that point, and then off upwards like that. And again, that line's a little bit too long for my liking, so I'll just trim that down a little bit. So this is getting steeper as we go up. I think we're going to find over here that, oh, what happened just then? I ended up skipping miles away from where I needed to be. Let's go all the way down here. There we go. Bump to the edge of the page. So when I go over to here, this is 2 times 1. So this point here is going to be a gradient 2, ranging from there up to there. I'll just draw a little short line, aiming for those, and I will erase those little target dots that I had there. This point here is going to be 2 times 2, that's gradient 4. So we're aiming from there all the way up to there. So we'll draw a little bit of a line in there that's aiming for those. By the time we get to here, we have gradient 6, so we're aiming from there to there. We're really steep by the time we get to there. I think you can see the idea of what's going on. Now, we would find a similar situation here over at the side, except it would be negative 1, negative 2, negative 3. This would be negative 2, negative 4, negative 6. What about down here with positive 1, negative 1? Well, that's a gradient negative 1, and then negative 2, then negative 3, negative 2, negative 4, negative 6. Over here, we're going to be back to positive gradients, though, because both coordinates are negative. Then negative 2, negative 6, negative 2, negative 4, negative 6. So you can see we've got a pretty interesting looking field going on there. Let's see if we can solve this differential equation now. So we would have dy over y equals x dx. Integrating both sides, the natural logarithm of y equals x squared over 2 plus an arbitrary constant of integration. Writing this as an exponent, we would have e to the power of x squared over 2 plus c, and that's best as a constant by e to the x squared over 2, and our constant here equals e to the c. So that's just a convenience. So this is an arbitrary value here. Let's pop over into GeoGebra and see if we can investigate this. So there's my slope field that we were just trying to draw. Looks pretty much the way we thought it would. And our let's set a constant. Now this constant could be anything, negative 5 to positive 5, it's controlled by that slider. Now we'll have our function of x, which equaled the constant k multiplied by e to the power of, we'll use some brackets, x squared over 2. Now, I happen to have k equals -1, and there we go. There's our particular solution if k equaled -1. What if k equaled 0? Well, that's our horizontal line where all of those slopes were 0 along the x-axis. Bit of a trivial solution. There's k equals 0.1. What if I can just animate those? Oh, isn't that beautiful? Look at that. All of those different solutions. Oh, I'm off the top of the page. Zoom out a bit. There we go. That's better. All of those different solutions represented by the differential equation dy dx equaled xy. Thanks for watching.